are the generators of this Lie algebra G, then normally this would all have degree 0, right? These are all, but once I put this 1 in here, I'm basically saying that these things here now have degree, I give them degree 1, so that they anti-commute and so on. So if I have that, let's try to construct, I want the differential operator of degree 1 constructed out of the only, what coordinates, so what coordinates do I have here? ZA, well, there's only one component, and I've called these coordinates already XA, sorry, X alpha, so that's the coordinates I have. So I can only create a differential operator by putting an X alpha here, where X, I've said, has degree 1, right? And that's what I've declared. So this thing here has degree -1. So in here I have to write something that has degree. In here I need something of degree 2. Well, what can I make with what I have here of degree 2? Well, I can put two x's, x beta, x gamma. Each of them is each of them is worth 1. So I have 1 plus 1 minus 1 is 1, and I'll put some combinator, some factor in front of this for combinatorics reasons, something like this. And if I impose q squared equal to 0, you can check that easily. What are you going to get? You're going to get conditions on f that are well, let's say the Jacobi identity conditions on f, where of course f are the structure constants of G, right? In the sense that tau alpha, tau beta give on the dual side f gamma alpha beta tau gamma, right? This is familiar, right? We've all seen this. Even if it's not, write down the q, square it to 0, and convince yourself that it's exactly the conditions you get from the Jacobi identity with general structure constants f.
Do you need something like reality or reality conditions on that?
No, not necessarily. I mean, not for me, not for now, not for me.
But I guess the fact that you put G in degree 1 means the x is anti-commute. Otherwise.
Yeah, I think even degree things commute and odd degree things anti-commute, and this is the convention we use. I mean, basically we need to call, basically we need to give these different degree objects, we somehow need to keep track of their behavior and parity behavior. Because like you could remember, we had the 1 forms and the 2 forms, the A's and the B's and so on. And so somehow the idea of grading, that grading is important in all of this is, grading is essential in all of this, and we just want to somehow keep track. This is a convenient way of doing things. The important thing, whether I give G degree 1 or 2 or 3 doesn't really matter, as long as when I add more terms, I keep alternating them, as long as I keep track somehow. Of course, how to write this with an even degree, how to do the Chevalier-Eilenberg complex and so on with even degree, I wouldn't know, but maybe there's a way. But this is, just think of it here as trying to keep track of all these different objects, like the 1 forms, the 2 forms, the 3 forms that we need for higher gauge theory, are deeply different in the sense of degree. They are smaller and bigger objects, and they behave different. 1 form wedge 1 form is different than doing 2 form wedge 2 form, right? So.
So the taus anti-commute?
No. It's just the coordinates. It's the x's. It's just the here. The taus remain. Here the x's get the degree 1. The taus remain neutral here. So the x carries the coordinate. Really think of the coordinates on the space, not the.
So the algebra elements are also of degree 1.
Yeah. Overall, yes. In this case, yes. Yes, actually, well, that's what it's written. Sorry, that's what's written here. We assume that in nature, normally, our G has no degree, and in these square brackets, I indicate a degree shift of 1 from the nothing to the 1. It's a shift because when I write, for instance, let's look at another example right away, so make it easy. Look at another example, which is also easy. T1 of some space-time sigma, of some manifold sigma. Now, what kind of coordinates? So I'm shifting the degree of the coordinates on the tangent fibers. So on sigma, I could have coordinates x mu as usual, of degree 0 as usual. But on this t bundle, I would normally up here have some, let's say, psi mu. Sorry, am I writing this? Yeah, because I would write a general element in here. I would write it psi mu d mu, right? Actually, c mu d mu if you want. Some coefficient, that's a function, times derivative with respect to x mu. Now I've shifted the degree, so I have made this guy into a degree 1 thing. So what happens if I take now functions of these coordinates psi mu and x mu? Since this psi mu now has degree 1, I want to expand this. I will have some f of x as usual, but this f here now it also has to somehow depend on these coordinates. And just like with superspace, for instance, since they now have degree 1 and they anti-commute, I have this is to write this expansion. There's only one way really to write it, and I end up, well, I sum it over different k's, but I end up with something mu1, mu2, all the way to mu k. And actually, okay, I could put a wedge in here even, because they are degree 1 and they anti-commute, so this makes sense to be, actually has to be written with a wedge, because if it was a symmetric product, this would all vanish. And I can, of course, I can have different psi, I can have one forms, let's say, let's call them like that, 2 forms, etc. And I'm not calling them by that by accident, because indeed, you can see that this is actually equivalent. I mean, in some sense, you can identify this space, the functions, so sections of this are actually, to all effects, p-forms on sigma. Because, sorry, this is a sum sigma, right? Not the because this is basically as if I was writing mu1 to mu k. I'm not writing any combinatorics factors now, times dx mu 1 wedge dx mu k, right? I mean, you know, there's no difference. These coordinates now, since I've given them, since I've shifted their degree, they behave to all effects like dx mu. And in fact, what is the q? So this is now so far we've got an n manifold. We've got a graded manifold because it is made up of sigma and the I don't know how to write this, but the sections, the T1 sections, let's say. I'm not going to write anything before I write something wrong. But the point is that this has now, okay, it's a graded manifold. It has coordinates of degree 0 and 1, and it also has a Q structure, which would be what? Well, what's the only thing of degree 1 I can make here? Where I can make a D on D x mu, and here I can put an x mu, right? But we say that this is the same as dx mu, D on D x mu. And who's that? That's D, right? And guess what? So that's okay, right? So that's just to say that also this space can be seen as an NQ manifold to all effects. Now this one has a body, of course, right? This has the body. This has the M0 that I didn't want to put before, but this is something we'll also use later. So let's immediately see it as an NQ manifold also. Might as well. And it's a nice example, yeah.
It's a bit unintuitive, the fact that we are constructing a general vector field with I don't know, coefficients that take values in the reals, but they anti-commute.
Don't have to be real. I mean, you can complexify that if you want. I think that's fine. Actually, I'm pretty convinced it's fine because the real hardcore guys, when they want to quantize those spaces I was talking about before, when they want to quantize, let's say, these n volumes, they use geometric quantization. So I think they complexify. They need to complexify everything by. There's nothing here to say. So far, this is just I mean, okay, this is an example. It's just a generic statement that an NQ manifold has those things. If it has those things, it's an NQ manifold. After that, we'll see. Then there will be NQ manifolds with extra structure, with complex structures, symplectic structures, metrics. You know, where we haven't yet given them anything else. This is what we have.
So the way I understand this example is you have the tangent bundle of sigma, which is a Lie algebroid with the anchor being the identity.
Yes.
And then there's this theorem that says that Lie algebroids are going to be in one-to-one correspondence with degree 1 homological vector fields on the dual.
Yeah.
Which is,
that sounds right, yeah.
which is exactly what this is, because you're talking about D now as a homological vector field on the dual, on the cotangent. Well, the cotangent as a supermanifold, so you need to take all the exterior powers.
So the Q is the dual to the Q. How do you say this? In the algebra, in the algebra. Once that's although I didn't want to go into the body example because you should look at it in terms of the DGA structure. Differential. How do you call it? Derived.
No, yeah, but
I mean, one has to construct it with more care. An algebroid, you have to get
But my question is, I mean, I would understand this from the dual point of view as the canonical Lie algebroid on the tangent model.
Yeah.
And the question is, in the general, but that's for this example. But in the general case, what is how do you view the general NQ manifold?
Dually. I mean, the dual would be the L infinity algebra for me, right? I mean,
so you have the L infinity algebroid
with no bodies. Algebra and with body would be the algebroid. But when you want to do that properly, you can't. What I'm going to, you cannot just say those m's of the Q are just the structure constants of something, right? You have to go into a whole, I can't remember.
Okay, no.
But there's it's in a paper. There's a canonical way to do it, which is old-fashioned as well. Getzler company, and so. But what I say now is not going to apply to the algebraic case, but it can all be done. Right. Yeah. So so that's an example. Let's forget about this because of the whole algebroid complication. But this is gonna appear again when we do our models, because what we're gonna be doing is we're going to be mapping to create models. I just mentioned it now. We're gonna be writing things of this type, and here I put a Lie algebra, but this could just as well be an L infinity structure or anything else. And this little map here will be what gives us our connection, as we'll see later. But I just want to say this guy will reappear, and we need to be convinced that the functions on this guy are indeed just the p-forms on sigma. Okay, so back to another example, which is a little bit less boring, of an NQ manifold. Will be one where n will be equal to, and I will write this now as w shifted by 1 plus v shifted by 2. Now I'm sorry about these degrees 1 and 2, because before I had my L infinity algebra always negatively graded, and now I'm grading them positively, so I'm giving the vector space w a degree 1 and my vector space v a degree 2. But that's because the literature is split in that way. Like on the one side, on the dual, on the one side and on its dual, just so happened that this is usually the conventions that are used. So I've always stuck to them to be able to make easy connections to other papers. So I stick to them now. But there has, of course, if you want to repeat some of these calculations and so on, you have to be careful with the grading and make sure you're not confusing things. But okay, when we take this, so let's call the coordinates on this side WA, and they have degree 1, and here we have VI, let's say, of degree 2. These spaces do not need to have the same dimensions or anything like that. They're just two different vector spaces as before. And I will have on here a Q. So what Q can I write? Well, it's a differential operator of degree 1, right? That's all we know. So we can have a D on DWA and only a D on DVI, right? This part has degree -1, so in here I need to put stuff that has overall degree 2 to compensate this -1. So I can put as before FABC, WB, WC, right? That's two 1s. F has degree 0, that works. And I can give another name. I don't call them M anymore, I now give them specific names just because here it's few of them. And here I put a TAI with a VI, and here I have something of -2, so I have to put more stuff in here, put some combinatoric factors that I'm just putting in, don't need, again, conventions. WC, and then plus, so this is 1, 2, 3, minus 2 is 1, we're okay, right? And then we can put an N, I, A, J, and I should have an I, A, J, because how else can I make a number 3? Well, 2 plus 1, right? So I can put 2 plus 1. Can you read? Maybe that's not so legible. Write this out properly, but anyway, you find all this, of course, in the notes. W, A, B, J, D on D, E, I. This is minus 2, 1, plus 2, minus 2 is always degree 1, right? Now, as with the algebras where F were the structure constants of some brackets, let's say that here, if I write something in W as WA with some tau A, not going to get into it, but now the taus are graded, and why? Just to compensate, just to go from negative to positive grading here. I'm not going to get into the details, again you find it in the paper. Let's not get bogged down on grading right now, let's just get the general idea. So I write something in W and something on V, in general just like this, the notation, and then I can say that, for instance, mu2 W, or let's say, sorry, mu2 W, tau A, tau B, because remember mu2 acts on the vector on the entry, on elements of the vector space, not on the coordinates, would be equal to F, A, B, C, tau C. So that's how I'm just identifying the brackets with their structure constants, right? Just as I do in G, I say, you remember tau, let's say, let's say sigma I, sigma J equals F, I, J, K, sigma K. You remember this from normally algebras, and the same way here, I'm just looking to give these guys all names. So this I called it N, A, I, J, lambda J. Mu 3 would be tau A, tau B, tau C. And this would be H, A, B, C, I, lambda I. So of course this is in V, this is in B, this is in W. And then what am I missing? Mu1 of lambda I will be equal to T, I, A, tau A, again living in W because we're mapping V to W, right? Does that make sense? Usual same old story, nothing, just giving everybody names. Now, if you, again, you can do this as a nice little exercise, set Q squared to 0 and see what happens, and what will you get? Guess what? The Lie 2 algebra relations for, mu1, mu2, you remember all these usual same old, and you should check, convince yourselves that this is true. So I'm basically just saying I have now a dual description of the L-infinity algebra in terms of these Q structures on Q manifolds. Why do I bother? Well, we'll see in a minute, because this is how it's much easier to do physics this way. I mean, if you could, our first approach was just keep the L-infinity structure and then just write actions and put in there anything we can put in there that we found somehow, that we made to be invariant, and just see what happens. But with this kind of setup, with this kind of structure, we can see we can actually find a geometric reason to write down certain actions rather than others, containing certain terms rather than others. So we'll see that in a minute. But since it's the actions we want to go to, we will also need something extra now. We'll need some sort of a metric, because in the actions we want to be able to vary, right? And fields we want to be able to multiply together. And we want to be able to vary with respect to one field or the other, etc. So we haven't yet, for now we just have an algebra, we don't yet have a metric on that algebra, right? So of course we want something that will be invariant under that same structure. So what we do is we introduce the notion of a symplectic NQ manifold. Nothing to do with those previous forget all that. This is something else. And this is just basically an NQ manifold, so an M with a Q, with an extra structure omega, which is a, let's say, a two-form. This is not, this should write this. I'll just write it in words, not make too many omegas. A closed, non-degenerate two-form on the curly M. Sorry, and this should have been not an M, but a curly M, of course. Sorry about that. The curly M always indicates the MQ manifold. So basically, if this had coordinates ZA, then omega can be written DZB. I write wedge like this, but of course these coordinates are graded, so you have to be careful, not to write 0 here. So this has to be according to the grading. It has to be non-degenerate, so it has to include bits of them all. But let's say graded antisymmetric product here. This wedge means graded antisymmetric product, so you adapt it accordingly. And so far, nothing happened. We've got a symplectic structure. But, well, actually, of course, if these coordinates were odd, or both of order 1, then this would be just a metric, right? This would be a non-degenerate symmetric structure on, would be a metric on a Lie algebra. If we were on G1 with coordinates W8 or just of degree 1, this would just be a metric on the Lie algebra G, right? As a way of pairing vectors, right? Because this is a two-form, acts on two vectors and gives a number, right? So what?
And by close, you just mean the round close.
Yeah. So I should say d omega equals 0. So yeah, with the d on this curly M, of course. So again, think of functions on curly M, and they are f of those ZA, right? That we wrote as before. There would be this kind of expansion, C1, CK, and ZC1, ZCK according to the grading. Here, accordingly, I should write it out. Because only if they're odd graded, you can expand it, or at least this expansion ends only if they're oddly graded, right? Otherwise, the even graded ones, the expansion goes on. But anyway, let's just say f of ZA, functions of Z, are functions on this M, where these are all the coordinates and all the bits of, remember that M is equal to all these terms, right? And thanks to this structure, you can now, again, as usual, you have something like, I'm not going to call them Hamiltonian vectors, but let's say associated vectors V to each f, given by df equals contract with vf of this omega, right? And that allows you to define a metric, and I'm going to put in inverted commas because it's not always it's not always symmetric, sorry, depends, by saying f with g is IVF IVG of omega, and I will say this is taking the product, an inner product between f and g, between sections over this real complex, whatever you want, sections over this curly M manifold. So that's basically some sort of that's a sort of metric structure, that can be also antisymmetric according to what kind of coordinates you have inside. And indeed, it translates on the dual side. Remember, we had, instead of M, we had this L vector space, right? This thing with elements LK in there, let's say, you would get, I will write it as this round inner bracket, which will have the property that L, okay, let me, L1, L2, these are just symmetry properties that they're written again in the notes. I write this one out, but the other one not so much. The other one is basically how invariant is the metric under these mu k brackets is what I'm writing here. And again, there is a -1 with a sigma that depends, on the degrees of all these li's. It's written out in the notes. It's long. It's not of any use now. Just to say that there are well-defined symmetry properties of this thing under this when this product acts on them. Oops. So here we'll have I don't know, k L0, Lk -1 with Lk, right? So this kind of symplectic structure, which we're going to need all the time, has a nice property of giving us a metric algebra and means that we know how to couple. If in an action we wanted to write, even from before, say an A couple, an A and an inner product with a B, and you remember this A, even in the strict case, this lived in G and this lived in H, we had to somehow decide how to multiply them, how to smash them together, right? If we wanted to be able to, and we needed to know how this behaves under the structures if we want to be able to vary the action, right? Because we're gonna, we might have terms of the type, and we will have terms of the type, let's say B with mu3 AAA. This is now the semi-strict case, and we want to be able to vary with respect to A, so we need to know how to pull this mu3 over to the B side, right? And this is what this allows you to do. So, and why do I know this? I failed to say this, is because omega has to be Q invariant, meaning LQ on omega has to be 0. And by curly L I mean the leader derivative along Q, which you know probably from the previous course is diq plus iq. D plus minus according to the grading, of course. Well, the grading of whom? Q has degree 1, so I guess this would always be a minus. Am I crazy? Well, this has to be checked.
Well, that's a plus.
It is a plus.
Normally,
yeah, but now the Q has degree 1, so there are two things of degree 1. So I think there might be. Anyway, to be checked. I didn't double check that. Sorry. But it's a leader derivative along the vector Q of that structure has to be 0. So it has to be invariant under that Q, which translates in the dual side to a specific type of invariance under all the mu k products. Okay? Makes sense? Okay. So I think. One more thing to say about the structure, about the symplectic structure. Omega. Having this Q, oops, is that A, B, Z, B. Having this Q and having these Hamiltonian, well, not Hamiltonian, associated vectors means that the contraction with Q of this omega will be equal to the D of somebody, and in particular we call this somebody curly S, because this is the fact that this comes from the Q is its Hamiltonian vector makes it special. So this function is special, and it will be it ends up being called a Chern-Simons element, but we're not, just call it curly S, and it's important. And of course you can also check that by all the definitions SS has to be equal to 0 because of course Q squares to 0. Right? You can check this easily. And if you want to do the calculation, go again to the case G, just a Lie algebra, and try to find out, try to see, well, okay, you can put some sort of a structure on this, why not? Say A, B, what do we call them? W, I think. Let's call them W now. Let's say this is the structure you have. You know the Q I mean, we've written it down n times, but you also should know it anyway. From just the algebra here, is this. So find S. That's an exercise you can do, and it's an exercise well worth doing, because then you can apply what you get out of here to the next section and deduce Chern-Simons theory in this setup, which I will show you now for how to construct in general topological actions.
So I suppose that Q now can be represented as bracket with S.
Yeah, worth mentioning. Q acting on some function of the coordinates on that curly M is basically the same as saying under this Poisson bracket. Actually, I should label it. This is always the one that comes from this symplectic structure here of S acting on that function, up to signs which I know. Right? This is just the same as symplectic geometry now done on a graded vector space. I think the structure actually has since it's a graded space, if it was oddly graded, it would have a different name. It wouldn't be called symplectic structure, but I don't remember. But there's, again, this is everyone has different conventions, and we decided to just call it symplectic, even if it's not necessarily antisymmetric. It could be a symmetric structure, and we just call it that because from context it should be clear what it is. But okay, so that's the ingredients so far. So the NQ manifold, together with this kind of metric that we can put on it, if that NQ manifold does allow for a symplectic structure, are the ingredients we need for our gauge theory. Of course, before we do gauge theory or high gauge theory, we still have to decide what is our internal symmetry group. But whatever it is, I say the general setup that we will be dealing with. So I will say this. Let's make it clear right from the start. This is topological gauge theory. No metrics in here. And this is actually, I often in papers call it a generalized AKZ construction, but that's a misnomer, because I think it was Attia and others that first came up with this way of this very nice geometrical way to construct gauge theory. So I think the credit is actually due to I don't remember who else. It was Attia and others, but it's also, again, this is, I think, should be written clearly in my notes. I think so. Okay, the way it works is that we start with that T1 sigma that I mentioned before, to be viewed as an NQ manifold, so with its own Q on sigma, which would be the exterior derivative as written in psi mu d on dx mu, where these psi mu's are of degree 1. And what else does it need? Nothing. That's described by that. Yeah, well, its coordinates, of course, are psi mu and x mu on the two parts. And on this side, we will have I'll just write L as in any kind of n algebra, which could be a 1 algebra, 2 algebra. So when it's a 1 algebra, it's just a G, but otherwise it's an L infinity, a truncated L infinity algebra with degree shifted by 1, so that I can put a Q on it. So here I will have I will say the coordinates. Or actually, sorry, I'll put the curly M from before. I don't know which notation is better, but okay, let me put curly M and say this has coordinates ZA, and let me say that I have this usual Q on M, that we were talking about before, right? That you have to construct according to what coordinates you have in your degrees, and we will write, there will be a map. A will be a degree preserving map between Q manifolds, but it is not a Q-morphism, and we'll see in a moment why. This is for now just a map. And so what else? What do we have to, nothing else, I think. We can check that in general, if I do Q at sigma after the pullback of this A minus this pullback of this A after the Q on the M side, in general, this on some coordinate ZA, what is this? Well, it would be the D after the pullback of that ZA minus the pullback of QM A, right? Because Q is roughly speaking QA D on DZA, right? So that's that. Is that convincing? Right? That's a general expression. Now, I said that A is a degree preserving map, and I will just declare that A pullback of a Z A according to the degree of this of this coordinate will have to be, I'll call it on the space-time manifold a curly A, and then I will have mu1 to the mu of, I'll just call the degree of that A, so for easy notation, and this will have to be, sorry. Okay, well, it's not really a mistake, because maybe you do believe me that it's the same as that writing sine, writing dx is the same, but okay. So I will pull this back to a general connection, let's call it, or let's just call it big curly A, which has to be a, if you want, a form or a function on T1 sigma, so a section of this bundle with overall the same degree as this ZA, and I can do that by making it into a, let's say, A form, for instance. I remember this is the same as saying this. So if ZA, of course, has, again, if we were in G, in adjusted Lie algebra, ZA had degree 1 and was actually not equal to ZA but to that WA that I wrote, that I called it before, then the pullback of WA can only be a one form, degree preserving, it can only be a one form, so it would have to be A mu, A dx mu, and this little A here is the little index from, something in here being, let's say, WA tau A, right? So far, so good. So why not remain directly on this Lie algebra side, which is the easiest to think about, and just say what happens to that, why did I say this is not a Q morphism? What happens if I write Q sigma after A star of that WA minus the A star of the Q on curly M of that WA? Well, luckily in this case we do know all the ingredients. So this is D on sigma of AA, right? Minus the pullback of what? I know QM for the Lie algebra, right? It was that easy thing that we know and love. That's it, right? Acting, because it's acting on, it's that vector acting on, that would be a D of dWA, acting on WA is 1, right? And the pullback of this by this is just, so this is D sigma AA minus plus 1/2. Yeah, I'm not so sure about the signs. With the overall, I put the index A up here, meaning you know what I mean, I think, right? Yeah. Okay. So lo and behold, what has happened? We accidentally wrote down the curvature of A, right? So that already makes one think, I'm looking for some sort of, you remember before I had said, I'm telling you B has a curvature 3 form called that I would call H, and this is what it is, and it is because I can't put anything, I can't let anything else act on B. Well, here it seems that it's no coincidence that the f of a one-form connection for a Lie algebra, for a normal Lie algebra, is exactly what we know it is, right? It seems to come out of a purely like kind of abstract reasoning, right? It just came out. So why not say that in general? So this was our normal Lie algebraic example. So why not say in general define curly f of any a, now the big A runs over all the z's, as just this failure of this map A to be a Q morphism. I'll explain in a minute, but what I mean is a Q if the map A was a Q morphism, this thing, okay, if A were a Q morphism, that's the definition of Q morphism basically, it would preserve the Q, right? As these definitions always go, it means it preserves the structure. It would preserve Q. F would be identically 0 always. But since A is not, something will come out of these pullbacks, and we'll just call that curly F. We'll just call that the curvatures, whatever it is. Because it works in one dimension, for one forms we'll just say fine, that's what we call it. And okay, but we would still like, the thing is we would still like a, so let's stick to this for a minute. So let's again look at another better example. We'll take T1 sigma and map it with A. Now not just to a Lie algebra G1, but let's take our little V1 plus W2. Wrong names. That's another thing, I always get confused, so do shout when this happens. So we'll take this as an NQ manifold on this side now, with the Q that we had written down. You remember it had an F, A, I'm not going to put in all the factors, but WA, WB, it had that T, which was basically the new one, you know, DWA, BC, plus all the stuff that was in there with the D on DBI, right? So we know it explicitly. Again, exercise, homework. That's how you do it. Just let whatever you don't want to do by hand, in the blackboard, just homework. So you can check what happens now. And here we still have the same. This still has its good old-fashioned D on sigma, the dynamic differential on sigma, as before. It's the same. And just check what happens if you do the D after the A star of a WA minus the A star of QA, and this is called this is the W part of this curvature, and then you do the same thing with in here a BI and here a QI, and this would be the D part of that curvature. Now, if we get rid of the mu3, we go back to the strict case, we can get rid of some stuff we can actually get rid of, no, we can only get rid of one thing in here, because only the triple, the WWW thing was from the triple bracket, right? So unfortunately it doesn't simplify things enough, but it's an example you can try and just convince yourself that these will just be exactly those curvatures I had written down before, so that for strict case, you will get again F, you will get actually, you will get F, let's say A will be the curvature of A minus TB, and then the F let's say I will be that thing I've written down, the B plus the action of A on B, I think it was. But anyway, you know, check. Well, you can do this. You can do this, and then you can write it actually down for the semi-strict case. But you see what I mean? I mean, do you want we can write it down next? We can do it like one step by step. But I'd rather just write down the result and say for the semi-strict 2 algebra, which is V1 plus W2, you will get an FA. So here's the coordinates W with the A index, and these will have the I index. So FA will be equal to, well, DAA plus 1/2 mu2 A, whatever comes out at the eighth direction, minus the T of B. Again, A. Actually, you can ignore this. Well, I leave the A in just to be very, very explicit. But and then you will have the curvature along the I direction, which will be dB plus mu2 A on B. Remember, this is just the action of A on B. And then you will have, now that it's semi-strict, we do have a mu3, and we can put A in here. This lives in W, this lives in B. And these will be our two curvatures for geometric reasons for a 2 connection, okay? Now, well, so far so good. How much time do I have left?
Like 10 minutes.
10 minutes, okay. So, unfortunately, I can't then go into great detail, but let me just say at this point, this is a good time to mention it. We can now also, in a very geometric way, say how gauge transformations will act locally, yes?
That T is mu1, right?
Yeah, yes. So in an effort to make a connection to before, I exaggerated a little bit. Yeah, that's a new one. So just to say, gauge transformations can now also, you know, before I just said check that the fake curvature still vanish, you know, check what can you do with a function in a 1 form so that the curly f, the fake curvature, continues to vanish after gauge transformation. Now I'll try to convince you that there's a geometric way to do this and to get you know, systematic, like an algorithmic way to get an answer for local gauge transformations. And that consists in saying, you know, what is really a gauge transformation? I'm not going to prove it to you in detail. I'm just going to convince you by starting with the 1 connection case and just saying it works there, so why shouldn't it work somewhere else? So I will say, instead of just T1 sigma, we'll take T1 of sigma times an interval 0, 1. So it's a bit like in our picture taking a T, well, I don't know if I can draw this, at 0 and then a T1, yes, it's badly drawn, but like as if we, you know, instead of just having the sigma manifold, we multiply it by an interval, and then we take the tangent bundle to this whole volume here, and we map with a map A hat from here to our Q manifold, or whatever our internal structure is here. And I mean by the hat that A, such that A at we parameterize this with some, I don't know, little s, so that A at s equals 0 will be the A from before, and A at, sorry, this is written in a stupid way, because it makes it look like A depends somehow. So A at s equals 0, A hat at s equals 0 is A, and A hat at s equal 1 will be some new gauge connection A. So you see the pullback of this A gives you the connections, right? So that's why I refer to it as a connection. And I say a gauge transformation goes from one connection A to another connection curly A. So it's as if from here I map to M with the usual A, and here I map to it with the curly A. this is still n. You know, I'm taking all of these maps, and now you can try to just also maybe, you know, I'd rather just now one can try to write down the hatted curvature, which will now be b on sigma after a hat minus a hat star after q on m of any coordinate. So now you basically have to parameterize this whole space here with, we have more coordinates on here, right? Here we had x mu, here we had x psi mu, but now we also have here, I've called it S. So let me call the, maybe I'll call it R, because that's what I'm used to. R, sorry about that. And I will call it R here as well. So R will go from 0, will be the parameter in that little interval 0 to 1. And in the tangent, in the shifted tangent thing, I will call his partner rho. So if this was more or less dx mu, you can imagine this to be kind of dr. And so those are all your coordinates, all these four. So basically, now when you pull back, let's say you want to pull back a coordinate of degree 1, then this will have to have a mu dx mu, but also ar rho, right? Or this could be x psi mu, sorry, a mu psi mu. Well, it doesn't really matter. You know, yeah, we shouldn't get into walk down in this. You can say a mu dx mu plus ar dr, right? And that means that, and the same for any other order of coordinates, you have to be careful that you now have, you know, one extra direction to expand in. And now when you do f will now also contain bits in f mu nu, psi mu, psi nu, but it also contains things of this type, right? We've just given one just one more direction. So now, so basically everything now has one more direction, and you will find, and you can do this calculation again for homework. Write this out just for the, again, let's just here focus just on the Lie algebra case, the simple one, I mean the easy example, and try to see that if you impose that this bit here, you impose that this mixed curvature terms be 0, you will get the infinitesimal gauge transformations for A that you know, in normal gauge theory. And then if you feel courageous, well, it's not really that much, it's a little bit more of a hassle, but you can basically then play the same thing with V plus W. You know, you have all the ingredients, you just have to sit down and calculate, and you will get an F mu R of the A part of the V. I made a mistake again. V1 W, no, V2. And this will be again A, and this will be I, the indices, and you will have an Fi mu R that you have to set to 0, but also an I mu R that you have to set to 0, right? And when you set both of these to 0, you will get the infinitesimal transformations for A and B. In terms of, now you will have two parameters. Of course, parameters will appear here, and what will they be called? This, in normal gauge theory, this would be your, I don't know if you call it lambda, if you're used to calling it lambda or whatever, your when you look at it infinitesimally, your gauge transformation parameter. And here you will end up with two of them. You will have a function in a one form, right? That will appear, and they will be, coming in the same way from AR and B mu R, right? Because here you will in the gauge theory case, you just have A mu and AR, and this guy will be the parameter. Here you will have AR, but also B mu R that are new. Basically, look for the new guys that come from that R direction and set, and those guys will be your parameters, that, you know, the generators of your transformations. So the point being that in a geometric way, I guess it's a little bit intuitive that if there exists, you know, a connection for this whole space, if I set to 0, like I say that the transformation from A to A tilde has to be flat along this direction, which is saying that F mu R is 0, that this would be like defining a gauge transformation. That makes sense, right? We're saying the gauge I mean, intuitively a little bit. If you can check the one connection case, see that this indeed does what it's supposed to do, and then check the two connection case and see how you get the same transformations I wrote down at the beginning with an extra mu3 term, which we now have because we're looking in general at semi-strict. And when I had written down those gauge transformations at the beginning, they were only for the strict case. So that's all done in the notes more explicitly. And let me just quickly make just a comment on how to construct higher Chern-Simons theories. So we have said that this is not a Q-morphism, but it allows us to define fake curvatures, etc. So that's already nice. But how can we get actions now? To get actions, there is this also very nice geometric way, which basically means that we introduce a new map between Q manifolds F, which now F is a Q-morphism by we construct it that way, because we will say, and here there will be a projection map, and we will say that F star after the pullback of the projection of some coordinate on M would just be equal to A star of that coordinate. So up here we will have this, if here we have coordinates at A, up here we will have the same coordinates at A, but then we will also have the ones that come from this tangent bundle shifted by 1, and so these would be like dZA in some sense, right? So we say that if we use F to pull back a normal coordinate, it's just as if we were going back via pullback of A. So nothing changes there, but we will define this in such a way that if I pull back dZA, I will get exactly that definition of the fake curvature, basically. So let's see if I want to write it down with the correct signs. Oh, God knows. So this would be, well, it's the same signs as before. So the A star minus A star after Qn on ZA, which basically guarantees that F star after Q is equal to Q after F star. So F star after Q, this would be the Q at Tm, and this would be the Q1 sigma, right? And so this is defined in this way. So that's a Q-morphism to all effects. Why do I want a Q-morphism? Because to construct actions, the way it is done now at this point is to say, what do I want an action to be? I want it to be gauge invariant, right? And I want it to be invariant under all this big new gauge structure, which is all these all these products and all these vector spaces and so on. So the way I do it, roughly speaking, is that I look for on this side here of the world, I look for Q invariant polynomials, they are called. Q invariant polynomials that I will pull back via this F to this world here, and being Q invariant on this side guarantees me gauge invariance on this side by construction, because that's what Q is. And so anything I write down in this way by pulling back these invariant polynomials, and on this side on this side here I don't only have MQ manifolds, but I also have metrics, right? I forgot to mention, but those metrics we talked about, those symplectic structures, they are available, and they get pulled back to here to inner, they will be the inner product here on between elements of different sectors of the algebra. And here, of course, I have the usual integral over sigma that I can take, right? So I will pull back invariant polynomials from this side to this side according to how high a degree I want this polynomial to be. That can be order 1, order 2, order 3. I would have to choose, what to integrate over on this side. So what degree action I will get. So a trivial invariant polynomial is the metric itself, like the symplectic structure itself, right? F star of that. And this will lead you to something like curly f, wedge curly f on the space-time side, and in the 2 algebra case, it will just be the fake curvature of A wedge that H, the curvature of B, for instance. But that, we say, is kind of boring. These are basically the higher generalizations of topological Yang-Mills, which is like saying f wedge f without any stars or metrics and so on. So that's, we say, is boring, as opposed to a lot less boring doing higher Chern-Simons theory, which, I mean, what is the hierarchy of boredom? God knows. But it is. But if you want to do Chern-Simons, instead of pulling back this symplectic thing, this symplectic structure comes from a symplectic potential, which you maybe also know from symplectic geometry. So this omega is equal to the d of some chi, let's say. And what you can do is you can pull back this chi. And to pull back this chi, why you pull back this chi? Because this is now not in and of itself something, this is basically, when you pull back this chi, you have to take a little bit of care, and this is described in the notes, to preserve the Q cohomology from the right-hand side with the, you have to preserve it on the left-hand side. So something that is Q exact on the right, you want it to be D exact on the left, so that, the structure is somehow preserved, the action, but for the action to be as invariant as you claim it to be by construction. So this chi, this thing here, will actually have to be compensated. So what you will do is construct something f star of chi, but you will find out that you have to compensate this with the pullback of that s, of that curly s, that is the Hamiltonian of the q on the right hand side. And this will give you what we call higher Chern-Simons theory. Higher Chern-Simons because that's how you construct it. Again, exercise. Play this game with a Lie algebra and with just a one form A, and convince yourself that pulling back that potential will give you exactly Chern-Simons theory. You know Chern-Simons theory. You know that it has that the equation of motion is basically requiring flatness of the connection. And if you do this just for the 2 algebra example, for example, you will find out that what it requires, the equations of motion require precisely the same higher flatness. So they require these higher curvatures to go to 0. Furthermore, this action you can, if you want to, if you are that quantistically inclined, reduce it to 0 dimensions. This can be done consistently in all this formalism, and you can then see that the equations of motion, that those higher flatness conditions are solved, lo and behold, by the emplectic manifolds I mentioned earlier, which is basically saying that those emplectic manifolds are a fuzzy version of something flat, right? So in some sense, all of this long discussion, to get back to the claim that the higher emplectic manifolds are in some sense the classic, the classical thing that has to be quantized into quantum field theories, albeit for now I'm only talking about topological quantum field theories, so these kinds of higher Chern-Simons theories. What's fun about this is that, for instance, for the Chern-Simons case, for the Lie algebra case, this method, if done a bit more rigorously than I now just kind of sketched for you here, can basically prove to you that in 3 dimensions there's only one gauge theory that you can write down with a one connection, and that is Chern-Simons theory. And then this, you know, some Chileans would be a lot less surprised that gravity in 3D is actually a Chern-Simons action, because you would know that there cannot be a gauge theory in 3D with a one connection that is not of that type, because it's that you're pulling back that invariant polynomial, and if you're rigorous with all your invariances, only one thing can come out. And this picture, this triangular picture with the, is a very easy way to basically, you know, pictorially prove that. There's nothing else you can do. And then the question arises naturally, well, in 4D, I will write my 4D Chern-Simons theory. If that's my only gauge field, in 4D, that's the action I can write down. With that, or with those two, sorry, with that A and B living in that two algebra and so on. Of course, as soon as you take other structures, who knows, but, you know, for now we're just arguing within this framework. So that's really all I wanted to say. So, well, it's not all I wanted to say, but, but it's what I have time. I hope you more or less believe me, some things.
Yeah, so questions are part of the question and answer session, which is starting now. But there is, let me see.
So I can go.
Wait.
I know they're for me, these questions.
1 minute only, there's going to be some coffee, so if anyone wants to run out and get one and come back, this is the time. If not,
I want to make a new mess for them.